Okay, so it looks like for the most part, everyone has a grasp of it, right? Maybe you don't um, understand it all, and that's okay, right? So the goal is just to kind of introduce us to some of these concepts, have us thinking about what are important things when we're working with machine learning, so that if you do continue on with this, you have kind of a head start and have some understanding. Okay. But this is good. It looks like at least no one said that they're lost, which is good. Perfect. Okay. So let me go back to our Google Colab. And again, hopefully everyone has that still pulled up. If not, I'll share the link again. And of course, I'll be sharing my screen as I work through it. So please make sure you have that downloaded locally if you do want to look at it later. But let's get started. So we looked at, of course, those few concepts that were important for our models. So, we looked at underfitting and overfitting and what that means in terms of how we're learning from the data. We looked at feature scaling and what we typically call, standardization or normalization of our data. And then last but not least, we discussed our train test splitting. And on top of that, we also looked at cross-validation. And we discussed a little bit why that was important, especially if our data is, kind of biased in a sense, right? The data is varying depending on the region that we choose from. So it's important to randomly choose regions from our data to train with, and then, of course, randomly choose regions to also test with. So with that all being said, keeping that in mind, let's talk about our three models for today. So we're going to start off with doing some clustering examples. So we're going to talk about k-means, which is a pretty fundamental clustering algorithm. Then we'll move on to Gaussian mixture models, which is a bit more complex, but still on this topic of clustering. And then we'll move on to our neural networks, which we will use for classification. Okay. So let's start off with k-means. So first, let's just discuss k-means really quickly. So we have already discussed clustering. And so we know that clustering essentially means we just want to group data points together. So data points that we know are similar in terms of features and things like that, we want to put them all in groups. And so k-means, what it does is it will divide our data set into k clusters, right? So k-means the k corresponds to how many clusters we want. And we're obviously clustering it based on similarity. And in this case, we talk about it in terms of distance, right? So what's the distance of a point to the centroid of that cluster? So as you can see in this diagram, if you've got all of these data points, once we applied k-means, what it does is it takes the distance from every point to the center of that cluster. So for example, here in the blue, the center might be here, and it checks the distance from every single point to this cluster center, right? And so whatever cluster the points are closest to, you assign it to that, right? So another center might be over here, and then a third center might be here, okay? So it says with these three centers, what are the nearest points, right? And so you can see all of these get matched up with this one, of course, because these are the closest ones. And then the same thing with the black, right? So all of these are the closest data points to this cluster center, right? Or we call the centroid. And so if we want to actually look at more mathematically how these steps are occurring, we can see down here. So this is, a diagram. This tells us the algorithm. So what you do is first you specify how many clusters you want. So you choose your K. Then you randomly set the center of each cluster, right? So you initialize, which means we, for example, choose random points. So for example, in this graph, maybe you choose a random cluster here, random cluster here, random cluster over here, right? And then what you'll do when you choose these random clusters is you're going to assign a bunch of points to the nearest cluster. So for example, this cluster, maybe you get some of these points, right? And then this cluster, maybe you get, I don't know, a few of these, and then this one, you get all the rest of them. But this is bad clustering, right? This does not look very good. Does not look like the graph on the right. So once you've done that, you created random centers and then you cluster, you repeat this over and over again, where once you assign all the points, you're going to compute a new center based on all the data points. So for example, in this one up here, maybe I'll change my color. Let's do like the pink, right? So if I choose this cluster, what I'm going to do is this center is going to shift, right? Because all the data points are right here. So this center might shift to be over here, right? Because it wants to be in the center of all my data points, right? You find the center of all the data points in that new cluster you made. So in this entire circle, there's all these points. I calculate the mean of these data points and I put my cluster there. So the cluster, the new one, probably goes here. And so what you do is this one gets lost. You now have a new cluster there and it forms a new cluster now, right? So you can start to see now that's how that gets formed, right? So the centroid gets moved and then you repeat the process again. So once that centroid got moved, this one probably moves over towards here, right? Because it wants to match these data points. So maybe I go here. This one maybe goes over here. And then I repeat my process, right? So let's erase this, erase this. I cluster again. So maybe this goes there, this goes there, this goes there. It computes it one more time. Maybe this center gets pushed over a little bit, right? So once I do it there, you know, this one is a little far on the left. So maybe it centers back here. This one, of course, probably centers over here as well. And the other one looks like it stays about the same. Okay. So mathematically, that's our approach, right? You set a random point where the center is, and then you just calculate new centers and cluster over and over again until you stop, until basically those cluster centers don't move anymore, right? Because once you set up this center, these points down here will never assign to this top cluster, right? Because this point is obviously way closer to this than it is to this one over here, right? So eventually your clustering will stop. And that's when you want to kind of stop your algorithm. You say, hey, I've got my clusters how I want them. These are going to be the final clusters we have. Okay. So that's the process, right? Random assignment of the center, start making the clusters, move the center of the cluster over and over and over until you reach a point where you don't have to move them anymore, right? All the data is exactly in the cluster you want. So it's a pretty basic one, right? And so it's just this algorithm. It's what we call an iterative algorithm because it repeats, right? It iterates. It goes over and over and over again until you reach your final result. So with that being said, let's take a look at how to do this in Python, right? We're going to use sklearn today to implement this k-means. And again, we don't need all of this math, right? So this you could implement by hand if you wanted to. If you do take maybe a machine learning course in school or anything like that, you may have to actually write this algorithm on your own, right? Implement your own k-means code. But we're going to keep it simple. We're going to just use the k-means function, which already has all this math figured out for us, okay? So we don't have to do any extra crazy work. We're just going to say, call the k-means function and use it for simplicity. So let me clear this off and let's take a look at some Python code. So I'll walk you through piece by piece what we're doing for each one, okay? So the first block we're going to do is I'm going to import sklearn. Of course, we talked about this. This is where I'm going to be getting my functions to actually do k-means. And then I'm also going to import matplotlib, which we've talked about last week. I think Joseph kind of started off by talking about matplotlib. So I'm going to import that as PLT. So whenever I want to use it, I can just type PLT instead of having to put this kind of messy matplotlib.pyplot every time. Okay. So I'm going to run this. And now I want to generate data that I can use to cluster. Okay. So the way I'm going to do this is I'm going to use a function from sklearn. It's called make blobs. And you can imagine what this does. It's going to make blobs of data. So I'm going to import it. And then I'm going to say, hey, let's imagine I want to create 4 clusters. So I wrote some code here, cluster number equals 4. So I want 4 clusters. And then what I'm going to do is I'm going to make some data, make some blobs of data where there are 4 centers, right? 4 cluster numbers. There are some other parameters. So this says I want 500 points, right? 500 random points that are with 4 clusters. And then there's some information, right? Random state and my standard deviation of the clusters. Those you don't need to worry about. If you want to, you can mess around and change some of those numbers. I think those are interesting results. But for now, just focus on me making blobs of data, 500 data points, 4 clusters, okay? And what I do is I set that equal to the X and the Y value. So these blobs will create the points, and then it'll create which cluster those points belong to. Okay, so let me run this. And what I can actually do is I can add some code and I can actually print, let's do print, let's just print X, right? So what I want to do is I want to show you what these become. So if I print X, these are all the data points, right? These are the X and Y points that I have. And then if I print the Y true, these are going to be the clusters that it's in, right? So the first data point was cluster 1, cluster 1, cluster 0, 0, 1, 2, and so on. And so hopefully everyone can understand this, right? This is the X is the data, Y is the label, right? What cluster it belongs to. And then down here, I just basically kind of flip the X values here. So this is a little trick that it just looks better plotting. This isn't too important. I just did this for my sake. So if I have this, I'm going to delete this here. What we can see is that now I want to plot the data. So I generated the data using my make blobs function. Now let's actually plot the data using matplotlib. So I import k-means. So of course, this is the function I'm going to use to actually create the k-means algorithm. So here we go. I let k-means equal k-means, where I put the cluster number. Remember up here, I said cluster number was 4. So this says create a k-means model with 4 clusters and a random state of 0. Again, that's not too important here. And then once you have this object, right, I've created this model and I saved it as k-means. Then I want to fit my data to this model. Okay, so remember I had X up here. X was my data. I'm going to fit my k-means model to X. And then once I fit it, I want to predict those points, right? So once you have the model, it's been fit to the data, then I want to predict my my model, what the output's going to be for that data. So here I just do, dot fit X, and then I dot predict X. So that'll give me kind of the labels for each of these. So where, what cluster is what. And so here I go and I create a scatter plot, right? So PLT, which is for my matplotlib. Okay, so plt.scatter will create the scatter plot. And so what I do is I plot the X and the Y values. Remember, X up here, which was my data points, had 2 columns. Okay, so I remember when I plotted it out, I can kind of show you again. It has 2 columns, right? So it has one column that's going to be the X value, and it's got the other column that's going to be the Y value of my data. Okay? So you have 2 columns, X and Y values. So with that being said, when I want to plot it, I need to call the first column, so column 0, and then I need to call the second column, column 1, right? So this says take all the rows in the first column, those are my X values, take all the rows in the second column, those will be my Y values. Okay, so scatter plot with X and Y. I've got my labels, right? So that's kind of going to give me the color. This has a color map to it. That's what's creating these kind of nice yellow, green, blue purple. And if I run it, so I already ran it, obviously you just saw it, but if I run it again, you get a plot like this, okay? And so what you can see is that from the labels, we would expect this data to indeed have those 4 clusters, right? We made it so that it had 4 clusters. This data looks like it has 4 clusters to it, okay? Really quickly, I can draw those, right? So we imagine maybe this is the first cluster, this is the second one, this is the third one, this is the fourth one, right? So 4 clusters, just as we expected. Now, all I've done is plot it, right? I haven't actually, I haven't really done too much, right? All I said was, hey, this is the data. I made some blobs. These have these labels. Great. But let's kind of dive into how k-means work. So k-means creates these circular clusters, right? It's everything is a circle, okay? If you go higher dimensions, we're only going to work in 2D. When you move higher dimensions, it gets a lot trickier, but everything is going to be a circle, right? If you go bigger, then it turns into a sphere, right? So a circle in 3D would be a sphere, and if you go higher, it could be a hypersphere. But k-means are circles, right? They create circles around your data. And you've got a radius that's going to be defined by the most distant point in your cluster, right? So remember, the centers of your circles, of your clusters, are defined by the mean of all the points in the middle. And that's going to create a cutoff, right? So if you find the distance to the farthest point, that's the cutoff of your radius, right? So that creates the circle. Any point outside that circle is not a member of that cluster, of course, right? So if it's not in the circle, it's not in the circle. It's not that cluster number. And so what we can do is, I've kind of put some code here. You don't need to know how to do this. This is a bit more complicated than what we'll talk about. But for visualization, I added this. You can see the circle clusters. So if I run this one more time, and maybe I zoom in a little bit, you can see how we've created 4 circular clusters, right? So we've got 1, 2, 3, 4. And some of them actually overlap here, right? So you see in some of these regions, we've got a little bit of overlap, right? And that's okay, right? For the most part, your cluster sphere might overlap, but the cluster assignment doesn't overlap, right? You're always going to be assigned to one specific cluster, right? It's always, you're for sure cluster 2, right? I set you to cluster 2. You might have maybe clustered it wrong, right? So maybe one point was put in the wrong cluster. That could happen, but it's still in that cluster, right? There's no ambiguity as to where it's in. So these are the 4 clusters. And let's see if I can zoom out a little bit here. So we kind of pose this question. We say, okay, looking at this, does anyone see any problems that might occur when we're using k-means? So remember we talked about k-means form these circular regions, and all the points have to be hard defined inside one of these clusters. Can anyone maybe think of a reason why k-means might not be the best approach given that information?
We could have clusters, but they're not circular. Like if we had like essentially lines or something as the groups of data.
Yeah, exactly, right? So that's one thing. If our data doesn't look circular, then k-means is kind of not going to work too well, right? Anything else? That's a really good point. And that's what I was looking for. But does anyone have any other idea? Okay, so something I'm thinking of is, remember, the clusters are hard to find, right? Not hard to find. They're hard to find, which means that you're set in this cluster and only this cluster, right? So if I do this k-means and I find a point, I say, oh, this point's automatically in cluster 2. There was no ambiguity as to, I thought it might be in cluster 1, but I put it in cluster 2 because of this reason. You don't have that information, right? All I know is it got put in cluster 2. But I know that some points might be on the edge, right? There might be points that I say, hey, I'm not really sure where it goes. That could be important information, right? If you're trying to categorize things and you have some, you're not too confident, we want to know that you're not too confident about that, right? We don't want you to say, throw it somewhere, right? So as of right now, it looks like we have 2 issues. 1, I don't like it being circular. And 2, I don't like how it's so strict. There's no room to say why things were put where, and kind of a probability as to where I expect it to be. Okay. So let's touch on one of those points, which is the circular case, right? So an observation we have is that k-means clusters have to be circles. There's no built-in way to deal with things that are maybe elliptical, right? So that we have these ellipses, which are a lot, wider and stretched out circles in essence. And so if we run this down below, right? So I run this, which actually just stretches my data. You see, if you do our clustering with k-means, it doesn't work too well, right? Our data is kind of oblong, right? It's got this elliptical shape, and it looks like you're kind of putting all our clusters together, right? We're overlapping a lot, which is not good, right? Because how do you know what cluster was supposed to go where now, right? There must be some ambiguity in where the clusters are going, because now you're dealing with circles when our data is really not circular. So with that being said, there might be a better method, right? So if you know what your data looks like, so here, if I took data and it was circular, like up here, good, we could do k-means, no big deal. But if you know your data is not circular, if your data looks like this, then we need to say, hey, k-means might not be the best method to cluster. Let's try a different method, right? And the different method to solve some of these issues that we get is going to be a Gaussian mixture model, okay? So let's take a look here. So like we said, we've shown that k-means can cluster, and it's a pretty good technique. But k-means obviously has some issues, such as hard assignments. So all the points are definitively assigned to a single cluster. There's no kind of, probability that I think I put it here. I'm not really sure. So what if the clusters overlap? We looked at that, right? Obviously an issue. And what if the data is not circular, right? What if it's spread out, and assigning clusters like that doesn't really work too well? That's why we look at Gaussian mixture models. So Gaussian mixture models are going to be able to extend our idea of clustering from k-means and give us this more probabilistic nature of the data. So I'll explain a little bit more, but yeah, it's going to hopefully resolve some of those issues we have. So let's start off with the basics. I don't know if anyone knows what a Gaussian distribution is. I'm going to assume that no one does, and I think that'll be easier, but if you do, this will be pretty straightforward. So a distribution by itself is basically a list of outcomes we have for our experiment and the probability associated with that outcome. So you can think of, if you flip a coin, right? There's a distribution of heads versus tails, and there's the probability associated with those heads and tails, right? So usually if it's a fair coin, you get a 50-50 distribution, right? 50% heads, 50% tails. For a Gaussian distribution, it actually has what we call a bell-shaped curve. So it's got this kind of little lump up and down, and you can see it here in this drawing. And so this Gaussian distribution, which we also kind of refer to it as a normal distribution, so these are, hand in hand, they mean the same thing. It's a distribution where half the data lies on one side and then half the data on the other, right? So there's this middle spot. So half the data is on this side, the other half the data goes on this side, okay? And what we see is that this distribution is actually split very nicely. This is kind of one of the favorite distributions that people use because of how neat it is, right? How beautiful it's set up. So basically, the center of your distribution is the mean. So if you take the mean of all the data, right, the average of all your data, that's the center point of your bell curve, of your normal distribution. So that defines the center. So right here, mu, which is the mean, is the center. And then your graph kind of decays outward based on the standard deviation of your data. So if you find the standard deviation, that's going to describe how spread out your data is. So if you go one standard deviation over, you'll get, if you look here, you'll get 68% of all your data, right? So if you were to just look at these main two blobs, you could get 60% of all your data right there. If you go out another standard deviation, so this is 2 standard deviations from your mean, right? So 2 to the left and 2 to the right, that's 2 standard deviations. You can actually get 95% of your data. So you get almost all of your data, just 2 standard deviations away from the mean. And then if you go 3, so if you go 3 standard deviations, you see it's starting to get flat, right? So you don't have a lot of data points out here. You actually get 99.7% of your data. So if you go 3 standard deviations away from your mean, you almost have all the data points in your entire graph, right? And if it helps, this distribution, you can kind of imagine on a number line. So what's happening is you have a lot of points in the middle, right? You've got a lot of points here, and then you've got a few less points out here, right? You've got a few other ones that are very spare, but you've got a bunch of points in the middle, right? So this is where the peak is, right? So you get low, you're getting more data. You have all the data, and then it starts to dive down again. You get less, right? So big data means big peak. Smaller data means you get lower peaks, okay? So that's how this works, right? And you can split it up. Okay, so that's just the basics of a Gaussian distribution. We're not going to go into any of the math or anything, but I want us to understand what a Gaussian distribution is, because our model is a Gaussian mixture model, right? So if you don't know what a Gaussian is, we probably won't be able to use this model. So this is the basics, okay? We've got these Gaussians, which have just this general shape. And these distributions are great when we have data that's really clustered together, right? We have a lot of data points which are going to create a peak, and then once the data points kind of start dying down, our peak also dies down. So you can imagine this might be good for clustering, because if we can find a portion, right, a large portion where all our data is really close together, this could create one Gaussian, right? You can create this curve around that data, and then maybe if you have more data somewhere else, you can create another curve for the new data that's over here, right? Maybe you have some more points way over here, so you can create more Gaussians over here, and you can keep making Gaussians for different clusters, right? So that's kind of what we're building on. I'll show another diagram soon on how we can visualize this, but that's the idea, okay? We're going to take points and we're going to fit it to a Gaussian, this nice little distribution curve. And right, that's for a single Gaussian. And then, like I said, if you want multi-Gaussian distribution, so you have multiple Gaussians, that means we have multiple peaks in our data, which have multiple centers. So we have, clusters. Data has this mean here, data has this mean here, and so on. So you've got different Gaussians for each region, right? Does this make sense so far? Does anyone have any questions before I keep going with this? You might still be a little confused, but does anyone have any fundamental questions? You're like, I have no idea what this curve is right now. Or does everyone understand we're basically just matching points to a curve?
All right, so are we taking, are you just introducing the concept to us, or do we have to take this to account when we're doing stuff in Python and AI stuff?
So when we're doing this in Python, we'll be able to create Gaussians pretty much automatically. So you won't have to worry too much. The idea here is just understanding the general shape of a Gaussian, because when you have a bunch of data together, so for example, back up here, you see this plot here. What I'm going to do is I'm going to try and fit a Gaussian to each of these. So maybe I'm going to create one that looks like that, another that looks like that, and then like that, right? So the goal is if I can make 4 of these, then I can make one big one that maybe has all of those features together, right? So I'm going to add all the orange together to make one big blue one.
All right.
Does that make sense?
Yeah.
Okay, cool. So yeah, that's my goal. I just want to understand, you know, if I have a general curve and I can fit it to one little piece of data, what if I just do it multiple times for different sets of data? Then I could bring them all together, and that would be a better model, right? If you create a bunch of little models and you put them together, it might tell us more information than if we just did one general one that, you know, it might get most of the data, but it's not very specific. We want to create a good model that's not too complex, but complex enough. So this is what a Gaussian mixture model will do for us. Here's a nice little picture, which I think is building on what you were asking, right? It's kind of more conceptual approach. So let's say I have data that looks like the red. So let me put a bunch of red points here, right? I've got data here, 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 whatever, right? And the goal is I want to fit all this data, right? Maybe you have some outliers. You always want to account for those, right? So we've got some outliers. And what you want to do is I want to say, how am I going to fit this data really well, right? And one approach we could do is just say, let's create one curve, right? If you want to create one curve for all the data, that could work. But our approach is we create different Gaussians that maybe fit. So you see here, this data looks like it has one peak. Oops, I wasn't annotating. So this looks like it has one peak. This one looks like it has another peak. And then we have a third peak, right? So you can see in the blue, I create one Gaussian that goes here, right? And then I create another one that goes here. And then I create a third one that goes up here, right? So I have 3 different Gaussians, right? 1, 2, 3. And if I combine all 3 of those together, so you just add all of them up, it turns into the red, which actually fits our data points really well. Okay, so the individual blue ones are just single Gaussians. The red one is our Gaussian mixture, right? It's a Gaussian mixture model. We modeled our data based on different Gaussians for different regions of the data. Okay. So this is kind of a simple example of if we have some data points and I want to fit it nice and neat, we create a few Gaussians, we add them up, we create the red. Now we can look at some other examples. So this is, you know, like I said, a pretty basic one. We can have a more complicated one, which is almost what I just drew. You see all the black points here, and maybe I can zoom in a little bit for everyone. All the black points are our data. And what I'm going to do is I'm going to take a Gaussian of the black, right? So the black curve is the first one. Then I'm going to do a Gaussian in the green. And then I'm going to do a Gaussian in the red. And I'm going to add all those together. So if you add the black, the green, and the red, you get this dotted blue. And the dotted blue follows it follows the data pretty well. Obviously, it's kind of shooting up a little bit in these regions, but for the most part, we're going to capture all of the data in it, right? There's this general trend where I can probably capture almost all the data points under this Gaussian. Okay, it might not be perfect, right? This Gaussian is obviously not perfect, but you can see what we're getting at. You're trying to fit the data to a few different curves and just combine it into one big curve so you can get all of the points together. Right. Another example, which might be a little tricky to see, is this one down below, which I actually like a lot. So this one looks at a few different Gaussians, right? So let me annotate here. So this one is for a 1 one Gaussian, this is 2, this is 3, and then it's 4, 5, and 6. So let's look at the one Gaussian model in the top left. If I create one curve, you see it misses a lot of the data. For example, it misses this region here. It misses all of this over here. So it's not great, right? It's not horrible, but it's not a great curve, right? I want to match all of the gray as best I can. If I can get a curve that matches all of the gray, that would be perfect, right? It'll get all those points. Let's move on to the 2 Gaussian model. So if you have 2 Gaussians, this looks a little better, right? So you've got one over here, and then you've got another over here. You add those up, you get the yellow. Again, it's not bad, right? We are missing some of this top area over here. So it's not perfect, right? I do wish this graph kind of had some shape like that. So maybe I want to move one more Gaussian, right? Maybe I want 3 Gaussians. Let's take a look at that. So if I move it 3, this is looking pretty good, right? You see, I'm pretty much going through almost all of my points. I'm inside that black region, and that's from a Gaussian that's here, a Gaussian that's here, and then a third Gaussian that's there. So this is looking promising, right? We've already went from 1 to 2 to 3, and 3 looks pretty good, right? We might be able to use a model that has 3 Gaussians. But while we're at it, let's just check the other ones. Let's check 4, 5, and 6. Let's see if those do a little bit better or not. So if you go to 4, again, we're missing a little here, but that's just because we're trying to perfectly match some of the other spots. So for example, you see how this point over here was a little bit off, and maybe this one as well. These are trying to account for some of that. And if they do, it kind of pushes this region down a little bit. So the 4, it looks like it's kind of trying to fit the data a little too much, but that's okay. What about 5? Well, 5 looks pretty good as well, right? So it's fitting our data pretty nicely. And again, 6, if you have 6 Gaussians, you can see how these are adding up, right? You have 1, 2, 3, 4, 5, and then one big one here, 6. If you add all of those together, you get that one, right? So what we're seeing is 3 might be good, 5 or 6 might be good. I don't really know, right? Depending on what you're trying to do with your data, 3 might be good enough, right? If you want something that's very general and it doesn't have to be too specific, 3 Gaussians might work fine. But if you need a complex, a more complex model, maybe we do 6 or something like that. But yeah, so hopefully this kind of helps a little bit more to see how we're taking all the Gaussians and adding them together to make one single curve, right? So this single curve is going to fit all the data we want. So from here, we can imagine that like I was plotting it in a 1D area, right? So if all of your data is plotted like this, right? So all the red points are kind of plotted, the green and the blue. You could create 3 different Gaussians based on those points. Where they're clustering the highest would be the mean, right? So if there's a lot in that region, it's the mean. And then it moves outward just like our normal Gaussian distribution would, right? Less points means the Gaussian dies off, right? Less points over here and here, our green is going to die off. Same thing for the blue, it'll die off. Okay. And so with this being said, why is this even going to work, right? We talked about, we want Gaussian mixtures to fix the issues from k-means. But how is it going to fix the issues from k-means? Well, it's going to fix it because if I can assign each cluster a Gaussian distribution, so cluster 1 gets this red distribution, cluster 2 gets the green, and cluster 3 gets the blue. Each distribution has a probability, right? So if you look at a point, you could give the probability that it's in this cluster, right? So if you take this green point right here, right? It's probably got a 99% probability that it's in cluster 2. But it probably has like a 0.005% that it's in cluster 3 and cluster 1, right? It could be in cluster 3 and cluster 1, it could. But the likelihood of it being in those is very small. With k-means, we never had that likelihood. We never said, it's very likely it's in 2, but it might be in 1 and 3. We never had that with k-means. But with Gaussians, we can find that information. We can say there's a probability for each point depending on what cluster it's in, right? So maybe if I look at, this point way over here, it's probably got a really low probability for all models, right? It probably has, let's say 30, it's not gonna be 30, but it might be 50% blue. And then let's say like, I don't know, 30% green, 20% red, right? That might not be the exact probability, but what I'm saying is you could take a point and you could get this. You could say, what's the likelihood it's the green cluster? What's the likelihood it's the blue cluster? And what's the likelihood it's the red cluster? And then once you have all those probabilities, that's how you decide what cluster is where, right? It's no longer the k-means, which is just what's the distance from the center, right? If you have a cluster here and I've got a point here, it says what's the distance from here to here? Is that closer than maybe another cluster center, the distance from here to here, right? For k-means, that was fine, right? But with Gaussians, we're no longer worried about this distance. We're doing a probability. We're saying, how likely am I here or here or here? And that gives us more information, right? That might be a lot more useful for you because sometimes you want to know ambiguity, right? Sometimes I want to say, what if I was over here? What if I was in cluster 3, right? Or what if I am in cluster 2, right? What does that mean for me? Okay, so this data could be important. And so Gaussian mixture models are going to give us this extra level, right? An extra layer of information, and it's probability. Okay. Before I look at some of the code, so we're going to do this in Python. Does anyone have any questions? Okay, so I'm gonna dive in. We don't really have a lot of time, so let me talk about these really quick. So with the Gaussian mixture model, again, I'm gonna import mixture. Mixture is one of the spots for the Gaussian mixture model. So what I do is I import it and then I load an object GMM, which is short for Gaussian mixture model, and I'm gonna make 4 components, right? 4 Gaussians inside it. So what I'll do is I'll fit it with my data. Remember, X was the data that I made way back when, right? I made blobs for my k-means. I'm going to use the same data from the blobs, okay? So this is just the same exact problem. We're just using a different approach. So let me fit my Gaussian mixture model. I'll get the labels for each model, and then I'm going to create my scatter plot, just like I did last time. And it looks about the same, right? Remember, this is a very similar plot to what we did with k-means. And because our Gaussian mixture model gives us probability, right? It's got this probabilistic nature. I can get the probability that each data point is in each cluster. So what I'll do is I'll use this function predict proba. Right? Predict probability is what it's standing for. And what it gives me is it gives me a matrix, which it gives me, the row stands for the probabilities, and then each column is the probability for each cluster. So here, if I run this, right, I predict the probability, and then I only give you the first 5 rows. So look, this is the first data point. The first data point says it's 100% in cluster 1, right? The first column is cluster 1, cluster 2, 3, and 4. It says the 100% in cluster 1, right? The data point 2 says it's 100% in cluster 2 as well. But then data point 5 says, I'm only 68% sure that I'm in cluster 1. I'm 31% sure I'm in cluster 2. And I'm 0.5% sure that I'm in cluster 4, right? So that's one of the nice things about this Gaussian mixture model. It gives us probability for each cluster. And that'll help us to kind of make a more informed decision as to what cluster I think it will fit into. And what we can do is we can actually try and measure this uncertainty. So when you talk about, for example, this point here, I said I was pretty sure that it was in cluster 1, but there's a decent probability that it might be in cluster 2. How am I going to look at that? Well, what I've done is I've plotted the same graph But anything that has a probability that's high, so if I'm really certain that it's in that cluster, the circles are big. If I'm not so sure that that point is in the cluster, the point's really small. Okay, so big means I'm in that cluster. Small means I'm not so sure I'm in that cluster, right? And if I zoom in, you can kind of see it a little bit better. You see this little small point here and some of the smaller ones here, 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 here. These are points that I'm saying, hey, they might not be in this cluster, right? There's a percentage of probability that might be in another cluster. We didn't have that with k-means, right? So this is important. We're getting more information from our data and we're able to make a better decision, right? We're more informed as to what clusters go where and what data points fit in those. Okay. So this is kind of a neat little way to try and visualize stuff. Remember, there's a bunch of techniques, right? So here I just kind of scale the data to show you high probability, big circle, low probability, small circle, but you could do any technique, right? This is just kind of one little sneaky way to do it. And of course, in the end, our goal is to assign each cluster, not with the circle or a sphere, which was what we did with k-means, but with a Gaussian. So what we'll do is, I've already written kind of a function down here that's going to help us visualize those, but it's not important, again, that you know how to type all this. I'm just going to give it to you so you can try and plot them. But let's say I wanted to fit a Gaussian to this. Well, let's run some of this code. And what I'll do is I'll fit my data and plot it. And so what you can see is that this is our spheres, right? So what we've got is each one is going to be a Gaussian, right? So they look circular because the data is circular, but this has a Gaussian that maybe looks something like that, right? So the outer ring has a lot less, the inner ring has a lot more of that data points. Same thing with everyone, right? So this kind of goes like this gets a lot, this gets a little, lot, a little, right? It's the same exact kind of approach for each of these. So each little blob has a Gaussian that gives us the probability that it's in those points. And with that being said, we could look at it in a better case, which is, you know, not when they're circular, because if they were circular, we probably could have just done k-means and gotten the same result. But what if the data was oblong, right? What if it was stretched out? That's a good case where we want to do a Gaussian because it might fit a little better. And so if we do that, we can plot it and you can see something similar to this. So this might work a little better. You see how these regions do a lot better at clustering. So it's not like this, 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 and this, right? With k-means, those are so overlapping. But with the Gaussian, there's very minimal overlap. You see that there's not really any data points in this overlap right here. Even in this region, right? There's very little data points that are in those kind of spots. So we're getting this kind of stretched out at which it corresponds to the same thing, right? You've got a Gaussian here, you've got a Gaussian here, you've got a Gaussian here, and you've got one more that's plotted down here, right? So using the same exact data we did for the k-means, we applied it to the Gaussian mixture model, and we got a little bit better results, particularly on the oblong data, right? So something that's not entirely circular, Gaussian mixture models perform a bit better in terms of how we're going to cluster them. Okay. But in the circular case, like, it doesn't really matter, like we talked about, right? The results kind of pretty much match up. You do get more information, right? Remember, you are getting the probability of each data point, but the clustering assignments are still the same, right? If something is 68% here, 30% here, you're probably going to put it in the cluster with 68%. So k-means would likely put it into the same region. So you're not going to get too much difference if the data is circular, like we talked about. Okay. So something important to remember, I think as Sean talked about, but we've been talking about it a week, is you got to understand your data and you got to understand what you're trying to do, right? Because if you knew your data was spherical, Why make a complicated Gaussian mixture model when you can just apply k-means? Okay? So just something to think about when you're going and trying to solve these, okay? So any questions with k-means or Gaussian mixture models before I jump into neural networks? Okay. So let's at least introduce neural networks. I don't know how much we'll be able to get through, but we'll see. I might take a little bit from the lab in the beginning just to talk about the rest of this. But let's discuss neural networks. So we talked about this a little bit yesterday, right? Sean worked through some neural network stuff. But essentially, neural networks are a machine learning algorithm that we have that mimics this kind of biological neural network, right? So you think about in your head, you have a bunch of synapses, and all of your brain is connected, right? You have a bunch of neurons that are linked together and you're sending signals all the way through. And in the end, you're able to perform some function in your body based on all those neurons coming together and talking, right? So it's the same thing with the neural network. We've got a bunch of different branches and they're all going to come together to give us different information. And at the end, we put all that information together to perform some task, whether it's, in this case, maybe you want to do a classification, right? So all the branches are going to send information about, I think you should choose this. And then finally we come together and we make a final decision on what we think is what. You can read about some of it here, but I'm just going to give you the basics because we're a little short on time. So neural networks are based on what we call perceptrons. So perceptrons are basically a little input-output scheme where you input a bunch of data and each input that you have has some weight to it. Okay, so you can scale the data however you want. So maybe you have some input that you put in that's really important, right? You have a feature that you say, this is really big. Maybe you want to weigh that feature more than some of the other ones. So you've got inputs. You can weigh those inputs based on how important they are. You've got a little bias if you need to input some other information, such as if maybe all the inputs are 0, you want to put a bias in so that you're not just having a 0 input. And then you've got this activation function. So all the data comes in and then you do something with the data, right? You've got a function that says, hey, take all this in, compute something, give me an output, right?
I have a question.
Yep.
So why would you necessarily need a bias? If you have like all zeros, for example, why would you want to alter that output?
Yeah, so sometimes what happens, especially if you have many layers of a network, as you get to the end, the inputs that you get are so small that they almost don't carry any weight. So at a certain point, you might reach where the inputs are basically 0 and your neural network might just die, right? Because you're not sending any new data. So what you do is you might put in a bias so that you're not just sending zeros, but you're sending actually some substance back in. So it kind of, like amps up your network again. Does that make sense?
Yeah, thank you.
Yeah. So we've got all these different ways that we can, send data in, and you can choose different activation functions, right? What you want to do with the inputs once you get them. We're not going to go into detail on those. There's a lot of crazy stuff that can be done there, but this is the basics, okay? We've got a perceptron, which takes it in, has some function to work with the data and output something. Now, you could combine a bunch of these perceptrons to create a neural network, right? So this could be one perceptron, right? Shooting out some information. This could be another one and so on. So you can stack these perceptrons together and you can create these neural networks. Now, with these neural networks, you can have something called hidden layers. And so with hidden layers, this is just how you stack on further and further. Hidden layers are stuff that you don't really see. So if you run stuff through hidden layers, you don't directly see the inputs and outputs, right? So all you ever really see is this and this, right? So you think about everything we did before. I saw the data and then I saw the graph of the output of my model. You don't see this stuff in between, right? So that's the same thing. In a neural network, all the stuff you don't see is called the hidden layers. So you do computations layer by layer by layer by layer, but you only ever see the input and the output. You don't really know what's going on in the middle, right? So that's just some terminology. You can have some hidden layers, and you can actually stack a bunch of hidden layers, right? So in this case, I only did one hidden layer, but maybe there's a nice little picture down here. You could have, you know, 2 hidden layers. So here's your input, you get 1 layer, then you send it to be another layer, and then you get your output. Or you could have, you know, hundreds of layers. You can just keep adding on. There are some benefits to keeping the layers small, and sometimes there's benefits to adding more layers. So we're not really focusing too much on that today, but this is the basics of our neural networks, okay? We're gonna take this input and output, and we're gonna do a bunch of processing on this in between in these hidden layers, okay? It's 12:30 right now, so what we'll do is we'll take our break. I am gonna come back at the beginning of lab and maybe take about 5 minutes or so just to finish up my conversation on neural networks. And then we will jump in with the lab assignment, which is implementing k-means. Okay, so perfect. We'll take our lunch break. If anyone has any questions, feel free to stick around and ask me. If not, I'll see you in an hour. Alrighty, see you everyone.